All right, well, I did lose a bet on the number of people that would be here today, so good job. I lost on the low side, so thanks for coming. Okay. Well, before we get to talking about gravitational potential energy, I just grabbed this picture, so it's not that great. So here we have a situation. So this is a review of the definition of work, right? So here we have a spring that's attached to a block here on one side and a wall on the other side, and being pulled by a hand to the right. So the spring is initially relaxed, and then you're stretching the spring. Right? You're pulling the block, which stretches the spring. So first, let's ask the work done by you or the hand. Right? Is that going to be positive, negative, zero, or does it depend on which way we define our axes? That it's the work done is positive. What's the reasoning for that? Yeah.
I said because the displacement is like going the same way as the force.
Right. So the force of the hand is to the right, based on our point of view, and the displacement is also in that direction. Right. So for work, that's what matters. Right. So if we define that direction to be positive, then we're going to have positive and positive. If we define that way to be negative, we're going to have negative and negative. Either way, when you multiply force times displacement, you're going to get a positive value. Now, if we remind ourselves of the definition of work that we've been using, we've got F, so work is equal to the force, however you want to arrange it, like cosine theta times the displacement. Well, if we think of theta as the angle between, so we can see that this is going to work even if you want to do it mathematically, right? The angle between the two is 0, right, if they're pointing in the same direction. So force points this way, displacement points this way. That means theta is equal to 0, and cosine of 0 is 1. Doesn't matter if you use radians or degrees, but I'll say degrees. So cosine of 0 degrees is 1, right? So this becomes positive force times displacement. If we have, well, what happens if we have a different situation? Okay, so, I guess it was active because I didn't actually put the check mark of which the right answer was. So the correct answer for this one, the work you do on it is positive because the block moves in the direction of that force. All right, now let's look at the work done by the spring, right? There's going to be some sort of force from the spring on the block, right? So same motion, right? The spring starts relaxed, and you pull it this way. So during that motion, is the work done by the spring positive, negative, 0, or does it depend on which way you find the positive x-axis to point? It's just the effect of seeing the results here, but again, take a second and talk to the person next to you. How'd you, well, things are moving towards negative, so so take a quick second and discuss with somebody why you voted the way you did, and you can alter if you feel the need. All right, so the block moves which direction, right or left? Block is moving right, and the force of the spring points left. Right, those are opposite directions. So the work done by the spring is going to be negative. And as I almost gave away as I was doing the math here, if we have force in one direction and displacement in the other direction, the angle between them is 180 degrees, and the cosine of 180 degrees is -1. Right, so this is why I say probably you can always use the mathematical definition, right? The mathematical definition has to be right, as long as you do the math right? But I think, particularly for work, it's easier to say, well, is it going to be positive or negative first, just based on looking at the picture, and then saying, well, okay, do I need to take any components of the force, right? If it's either pointing same direction or complete opposite direction, then you don't have to do any trading, right? You just say, well, it's either positive work or negative work. But if you have, displacements this way, if you were pulling up and slightly up and to the right, then you'd say only the horizontal part matters, right? And then take the horizontal part, but it's going to be positive number. If you were pulling slightly up and to the left, then you again take the horizontal part, but the overall work is going to be negative. Okay, so this shows us that we can have work that's done by two different forces. And in this case, one's positive and one's negative. Now, I didn't give any additional information to figure out how those compare, right? Do they, the value, are they the same magnitude or different magnitude? Even though we know that they're different, positive versus negative. So again, here I didn't put the check mark, but the correct answer is negative. So if we wanted to be able to answer that, we need a little bit more information. So if I said, for instance, the block starts at rest and it ends at rest. Well, now that gives us information about the kinetic energy, the change in kinetic energy, right? So I could say that the total work is going to be equal to the work done by the hand plus the work done by the spring. The work done by the hand is a positive number, the work done by the spring is a negative number. So if it starts and ends at rest, then that means that, well, the initial kinetic energy is 0, the final kinetic energy is 0. So the change in kinetic energy is 0. And we can use the work kinetic energy theorem to say that that's equal to the total work. All right, so the total work then is 0. So in that case, that means that whatever positive work that you do is canceled out by the negative work of the spring. Right? And all possibilities are available, right? You could say, well, in between, it started at rest and you made it move, right? So for the beginning of this motion, your work was bigger than, if I said, well, it starts at rest and then at the end of this motion, it's still moving to the right, then in that case, you'd have to say, well, it started with 0 kinetic energy and now has some positive kinetic energy. So the work done by the hand has to be bigger number than the work done by the spring to more than balance it out. All right, so if we have multiple forces doing work on an object, we have to add them up, taking care to make sure which ones are positive and which are negative. Okay, so this is our review of the definition, right? Force times displacement times the cosine of the angle between the two. That's the way that our textbook has it defined. Now, on Wednesday, we thought of, and here we thought of grouping the cosine theta with the force, right? And so saying that way we're going to take a component of the force that points in the direction of the object that the object moves, and then multiply that by the displacement of the object. But as we saw, we have the thing that we talked about with positive and negative values. And that the work changes the kinetic energy. Okay, but as we saw at the, that gray is not showing up. as we saw at the end of class last time, in some cases we're rather going to think about more of, rather than a component of a force, we'll think of a component of a distance. Right? So let's think about lifting an object. Right? If I want to lift an object, I'm going to have to do some work. Right? So I would put a force pointing up. Right? And if I'm working at a constant velocity, that means that the total acceleration is going to be 0. So that means that the force I apply has to exactly balance out the weight of the object. Now, of course, we know that I had to get it started moving, but we're only looking at the part like while it's moving at a constant velocity. So during that time, my applied force would be equal to mg because that's the weight, force of gravity on the object. Is that visible to you now with the dimmer lights? I'll have to change that for next semester. Gray. This template is not good. Okay, so the force applied is mg. And then if I'm lifting the object, I'm going to have the displacement I can call a change in height. Right, so that means that the work that I would have to do is equal to my force that I'm applying times the displacement. So the work is going to be mass of the object times the acceleration due to gravity times the change in height. Now, we can always do these problems by thinking about work. But a lot of times it's useful to sort of broaden our picture. Right? So rather than saying, well, I'm some external agent doing work on an object that's lifting it, and gravity is also, the Earth pulling on it, gravity is also an external agent pulling on the object, and it's doing negative work. It's sometimes easier to define a system. Right? So we define a system, and once we've defined that, it includes the object and the Earth, and then we can define a potential energy. Right? So rather than, so you have to decide when you start doing a problem, am I going to think about it in terms of work, or am I going to think about it in terms of a change in potential energy? So if I want to think about potential energy, I would say that the potential energy of that object as I raised it, as I lifted it, increased by a value that was equal to the external work done. So in this case, that's going to be mgh. Right, so now that we've defined that, we can just say, well, rather than thinking about work all the time, we can define a potential energy, we can define a kinetic energy, and we can think of energy moving forms going back and forth between potential and kinetic energy. Right, so the important thing is the potential energy is a property of a system, not just of a single object. Right, so as soon as I say, well, if I'm going to talk about gravitational potential energy, it's going to be my system is the object plus the Earth. All right, now the other type of potential energy in this class that we're going to define is spring potential energy. Right, so if there's, so for now we'll leave that out. But I can never include an external force, like a person in that system. But so here for gravity, our system is the Earth, which exerts the force of gravity, and then the object being raised or lowered. Or, in principle, you could be raised or lowered by a height of 0, in which case it's not changing. As you raise the object, you increase its gravitational potential energy, and as you lower an object, it decreases its gravitational potential energy. Right, so that takes care of the sign. So we're all going to agree again on whether the gravitational potential energy of an object, once we've agreed on our system, we're going to agree whether it's increasing or decreasing. And then that potential energy can be converted into kinetic energy and back again. Right? So here's an application. I remember my grandparents had one of these chain-operated cuckoo clocks. So you've got, for some reason, they're brass pine cones that are attached to a chain, and then so to set the clock, you have to pull down on the chain on this side, right? I always like doing that to the point where I wanted to do it even when it was already done, right? You do it once and then you have to wait however long, I don't know, 24 hours before you need to do it again. So you pull down on this chain, right? You're exerting a force downward, a displacement downward. So you're doing positive work on the weight, the mass Earth system, right? So as I'm doing that work as an external agent, I'm increasing the gravitational potential energy of the system, right? And then over time, now that gravitational potential energy is going to decrease, right? As this weight slowly moves down and makes the clock run, right? So that energy of the system is then, the part that's reduced by the as the gravitational potential energy reduces, that goes into the mechanical energy of making the clock move. All right, so we can see that whatever distance, as I pull this down, whatever work I put into the system increases the gravitational potential energy, and then later that gravitational potential energy, the same amount, is going to be used to run the clock. Right, so now we don't always lift objects straight up or straight down. Right, so this is the case where we want to group, or it makes more sense to group the force on its own and then think about the component of the displacement that's in the direction of the force. Now, it's not always going to be in the same direction, right? It could be opposite direction. But when we're talking about gravity, that is going to be the vertical component. Right, so again, work is negative when the force and the displacement point in opposite directions, but here you have to limit yourself to just the component of the displacement that is vertical when we're talking about gravity. All right, so only the change in height matters. So here's a little, the simplest geometric proof that you could ever do. All right, so if we say we start with an object here, and we raise it but also move it to the right, then the component that matters is just the height, right? So my displacement vector looks like this. If I'm talking about the work that I'm doing, my force is always vertical, right? So I want to get this component of the displacement, so that if that angle here is theta, then d cosine theta is going to give me the height, right? Don't get it confused with hypotenuse, unfortunately, same letter. But the height here is going to be d times the cosine of theta. So this is an example of why, when some people ask, oh, is cosine always go with the x direction? Not always. Right? Here we have the angle defined between the displacement and the vertical because that's the direction that matters for gravity. All right, so here's an application. So now at this point in 2020, it's kind of unrealistic to say that you'd be moving a huge old school TV like this into an apartment, but maybe we could say you're moving out of an apartment. But if you were trying to carry a large, or lift a large object from the ground floor to a, third floor apartment, oh wait, I just counted like a European. Fourth floor apartment, whatever. Up 3 flights of stairs. Either way. The change in gravitational potential energy is going to be the same between the two paths. So, gravity is a type of work where the only thing that matters is starting and ending points, which is what we want. This is when it's really useful to use energy. Right? All that matters is the beginning and the end. We don't really care about how it's moving in between. Now, okay, so if I'm looking at this, which is the way that people normally move things into and out of apartments? The stair situation, right? Now, the horizontal part of that doesn't matter in the case of calculating work, but we also know that there's more to it than that, right? Just when we talked about lifting weights, right? Just because you're doing zero work to hold a barbell above your head doesn't mean you can do it forever. You know, I'm not doing any work on a big TV while I'm carrying it horizontally. No work against gravity. But we know that just standing there holding it or moving horizontally is also going to take some effort from our muscles. So that might be one reason why I wouldn't want to carry it up the stairs, right? Even though I'm doing the same amount of work, I also have to hold it for longer, maybe. But here we have a case where, well, if I'm using a pulley, a single pulley system, that means that with my tricep, every time that I'm pulling down on that rope, or maybe more muscles, right? But whatever, I have to support the whole weight with a single group of muscles, right? So there's more to real life than just calculating and saying that the work done is the same either way. But the change in potential energy is independent of the path. So before we move on, I want to say one thing that we can say about this. Okay, so if the path doesn't matter, right, all that matters is the beginning and ending point, the force involved in that is called a conservative force, right? And in this usage, all that conservative means is just that energy is conserved. Right, so there are some forces, namely friction, that's the one that we're going to talk about, that don't conserve energy. Right, so when you talk about friction, you have to know about the path. Right, because if we think about, I used to think about this when I was commuting from Minneapolis to St. Paul on my bike, right, and I lived on a pretty high hill in Minneapolis. Well, the change in, from the beginning of the day to the end of the day, I end up at the same height. Right, so it should take me zero work to ride my bike. Of course, we know that's not true, right? And that's because there's friction, right? If you start at the top of a high hill, go down, and then come back up to another hill of the same height, you're not going to be able to do that without pedaling, right? Because you're going to lose some energy to friction, right? But it's not because of gravity. Gravity is a conservative force. The spring force is a conservative force. Those are going to be the main ones that we work with. And when you have a conservative force, energy is conserved, and you can define a potential energy. If there's a force that's not conservative, so that'll be like friction or like a pushing force, just some applied force, then we have to do work. We have to calculate in terms of work. All right, so let's start with let's apply this to an example here. So let's start with a roller coaster. So the roller coaster here, we'll assume that at the highest point, like this is the first hill, right? So you just get pulled up by the chain. Your velocity is basically zero when you get to the top. If you ever ride in the front car of the roller coaster, you feel like you're kind of hanging there for a while you're waiting for the rest of the cars to catch up, right? So we have a starting velocity of zero, and then over here we want to know what the finishing velocity is, right? And that's 20 meters lower than where we started. Now, if all we care about is the final velocity, we don't have to care about the fact that at some point in between, it was 25 meters below where it started. We can just ignore that. We can just look at the connecting the beginning to the end. Right, so the strategy, well, let me hide all that complicated stuff first and talk about the strategy. Again, when I'm doing the screen recording, I can't preview my next slide, so sorry, I have to go back and forth sometimes. So the strategy for solving a work or, well, any kind of energy problem is first define a system. So in this case, I'm going to define my system, and as I said, you can either talk about work or you can talk about potential energy for some of these cases. I would say that for most people, you want to define your system as broadly as possible, right? So if you can use potential energy, do it. So in this case, all we have is gravity. So I'm going to define my system as the roller coaster and Earth system. So that means I'm going to have kinetic energy and gravitational potential energy as options. Okay, so that's the first step, define system. Now I want to define 2 points that I'm looking at, right, and ignore everything in between. So for my roller coaster, that's going to be the starting at the top of the hill and then the ending over here. So this is just me, the notation I like to use, because sometimes you will then look at something that's happening at a third point. So I usually label them points 1 and 2 rather than initial and final. But that's, so I'll talk about E1 and E2 as opposed to E initial and E final. But however you want to do it is up to you. Right, so then at each of those 2 points, what is the energy? Right, so at point 1, I'll say I have E1. What kind of energy do I have? Oh, I guess one other thing that I need to define is where my 0 for height is going to be. So you can define it at any convenient point, but I'll define it at the ending point. Right? So all that matters is the change in height, so it doesn't matter where you call 0. Right? If we knew where the ground was, we could call the ground 0, but we don't actually know that here. Or we could measure from sea level, but I don't know if this is in the mountains or if it's in the Dead Sea, right? So you can define your 0 to be wherever you want. You might want to define, eventually we're going to go back and calculate how fast is it going here. Then you might want to define that as height equals 0. Doesn't matter. We'll all get the same answer in the end. Okay, so at each of these points, I might have some kinetic energy and I might have some gravitational potential energy, and that's it. So at point 1, I can say, well, I'm going to have kinetic energy at point 1 plus potential energy due to gravity at point 1. And I've written down every possibility, even though I'm going to go back and say, well, this kinetic energy is actually equal to 0 because the velocity is 0 at that point. Right, I'll call it V1 is equal to 0. And so then, okay, I'm going to have some gravitational potential energy that, based on how I defined my 0 height, the gravitational potential energy is not going to be 0. So then at point 2, I could say, well, what kinds of energy do I have? I could have kinetic, right? I definitely will. And then I could have some gravitational potential energy at that point. But again, I'll cross this one out and say that this is 0 because I've defined my height equal to 0 there. So this term is equal to 0. Okay, so now I've got my energy defined at points 1 and point 2. And then the next step is to say, is there any external work? Right, so is there any force that's outside of my system that's acting on my object? Because if so, that's going to lead to a change in the total energy. Right, so now we don't have just the work changes kinetic energy, we have external work changes the total energy of the system. So I would say here, the external work, it's equal to the change in energy, total energy, which is going to be equal to E2 minus E1. Now in this problem, we're ignoring friction, so I don't have any external work. Right, so here, external work is equal to 0. So that means that the change in energy is 0, or another way that you can say that is energy is conserved. I start and end with the same energy of the system. Right, so when I do that, that equation there becomes E2 equals E1, right? And E1 was just mgh, where h is 20 meters, right? It's just potential energy. And E2 is just kinetic energy, 1/2 mv squared. Right, so we can set those equal to each other, and the good thing is that the mass is the same on both sides, so it's going to cancel out. And so I don't need to know the mass of the roller coaster to know the final velocity. So we cancel the mass, solve for v, which ends up giving us the square root of 2gh, and that gives us a final velocity of 19.8 meters per second, or with sig figs, probably round that to 20. All right, so this general strategy, I always want you to, even for these ones where you can define your system to include everything, it's always a good idea to say, include the external work, right? External work gives a change in the energy of the system. For now, in this case, that change is 0, right? But you might have, for the first homework, it's just about work and kinetic energy. So your system is just going to be a single object. Right, so the work is always going to change. If there is some non-zero work, it's always going to change the energy of the system, and in that case, it would be kinetic energy.